All right, so just a couple of housekeeping things before we dump it or dive into material. That first quiz is going to due at the end of the day on Sunday. So you've got those practice problems that I have up there under the module. I apologize. Originally, the answer key was under the files tab, but I didn't realize it wasn't showing up under the module heading on the homepage. So you've got those two files now showing up on the homepage. I put those up there yesterday. Or I didn't put them up there under the files tab. I just added them to this homepage. So those will be kind of very good questions that prepare you for that first quiz. You also have that first problem set that's due by when? Time we start class Tuesday. Okay. Now I probably wouldn't hold off and wait and work on Tuesday. I put it to be before meet class so that hopefully any last minute questions you can stop by office hours on Monday, get those answered. So anything that I ask you to do in that problem set should come from this review of statistics due file. All the linear regression stuff that we did last class, that was after I kind of signed that problem set. And so you shouldn't need anything on that regression file. Everything you need should be on that review of statistics file. Yeah.
Right now, it says quiz 1 is due at 9:45 a.m.
I must have it set for my other section defaulted. I'll get it to change to be this section's class time. Thank you. But yeah, it's due before we meet in class on Tuesday. Any other questions? Yeah.
Okay, quiz. Do we need to also know how to do the practice problems for the second set of practice?
Nope. So this kind of quiz, since it's already been up there after class, this set of practice problems, you look at it, it's all about linear regression. So these first two quizzes are going to be a little bit closer just because it takes a little more time to kind of go through all that review material. Generally, they're like more spaced out every 2 weeks. So all the review of probability statistics, that's all quiz 1. Anything that we're talking about from last class to this class about linear regression, and it will extend a little bit just based off the section I had previous. We probably won't quite get through everything today. So I probably won't post that second quiz until after class Tuesday. But if you want to get it, you can work through probably the first, I don't even remember how many questions I put in here. They put like 20 or something. Maybe not quite that many. This is going so slow. However many questions are in here. All right, but 12. The last couple, maybe you're not quite sure on, but we'll make sure that we finish up everything in class on Tuesday, and then you should be set to go to take that quiz. But if you want to start looking at them early, that's what those practice problems I put up there for. Yep. Any other questions from me before we kind of get going here today? So, I mean, really, it looks like you have a grade in this class with these in-class quizzes. I'm going to eventually change things around in the grade book. Those were, if you go back to the syllabus, those are just extra credit, right? And so we just don't have any grades yet. So once we have those quizzes and problem sets come in, I'll rearrange things, going to have them weighted according to the syllabus. And then I'll also kind of get those so that they aren't factoring into your grade because they will just be extra credit points added at the very end. Okay. But they'll still have you'll be able to see them there. They just won't be kind of getting added to your grade yet. Okay. Files that we'll need today, this birth data and COVID data, regression due file, which I already have kind of pulled open here. We left off a little bit further so we can maybe take a little more time here today. We talked about this, and correct me if I'm wrong, I mixed up the other sections. I thought for some reason we went a little slower here, but we actually got through this example where we started to look at some very basic linear regressions, and I had my dependent variable, which was income. I had an independent variable, the thing I thought was causing the Y variable to change, which was the number of days the person used marijuana or self-reported marijuana usage every month. Want that going off during class. So we said, how do we interpret these values that we were getting from Stata? So the actual equation that we were estimating is this. So the intercept or the constant coefficient, the value that we got from our sample data is right here. The value that we got for this estimated slope between these two variables was reported right here. How do we interpret them? We said for the intercept, the interpretation is always this is the predicted Y variable value when the X variable is equal to what?
0.
0, right? Because if this is 0, 0 times anything is 0, my predicted Y value would just be that intercept or that constant. Okay. How do we interpret the slope coefficient? It was a 1 unit increase in our X variable would cause the predicted Y value to change by whatever that coefficient is. Now we don't say increase or decrease because this coefficient can be positive or negative. right? So here, if someone self-reports using marijuana one additional day every month, we would predict that their income goes down by about $253. That's our kind of interpretations, generalized, but also in the specific example. Okay. So that's these, right? I think that's where we ended, right? We had that example. So let's look at a different example and get some practice just making more interpretations. So let's say I have the following regression. I want to try to estimate, I have data, county level data, and it's got the number of cases per 1,000 people, and it's also got the percent vaccinated. Okay. So that X variable is measured as, 5%, 6%, 7.43%. If I'm looking at these results here, well, we can kind of see them. So how would I interpret my intercept or my constant? This is going to be the predicted value for Y if my X variable is equal to 0. So a county with 0% of its population vaccinated, we would predict the number of cases per 1,000 people is about 50. Okay. How would I interpret my slope coefficient? For every additional unit, 1 unit increase in X, or every additional 1% of the county's population that's vaccinated, we would expect the number of cases to fall by about, what, a quarter of a case, 0.25. So this is how I interpret my slope and intercept coefficient. Now, if this is the effect of a 1% increase, what if I wanted the effect of a 10% increase? What would I do? It's not a trick question.
Increase.
Huh?
Increase.
Yeah, increase it by 10, or what would I do? I could take that coefficient and this is the effect of 1%. How would I get the effect of 10%? Multiply it by 10. You just scale it up to whatever you're interested in, right? If I wanted the effect of 14.3%, this is the impact of 1 unit, 1% here, percent is the unit. I would just take that slope coefficient, multiply it by whatever factor I'm interested in finding the effect of, okay? Any questions? So I think got that here. Any questions on that one before it shouldn't be too bad. Okay, so the next thing we're going to talk about, I think I might have done this, but it's probably not harmful to reiterate it because we might have some examples where this occurs. I think the example I used last class was the years of education and income. So let me think if I can think of another one. Might seem stupid, but height and weight. So here's my scatter plot. Here's my line of best fit. Notice if I had a data set with height and weight in it and I ran a regression, unsurprisingly, I'm going to find that there's a positive relationship that the taller you get, the more body mass you have, you're just going to weigh more on average, right? So my slope coefficient is just the slope of this line. My intercept coefficient is where when that X variable of height is equal to 0, where does my predicted Y value start? So my intercept would be down here. Now, this is a what value? Negative. So the interpretation here, let's just put a number to it. I don't know, let's say it was -10, right? And we're measuring weight in pounds and height in inches. So that would be for someone who is 0 inches in height, her predicted weight would be -10. Well, how do you have -10 weight? I mean, maybe if you're in like right, some type of anti-gravity or something. So sometimes these intercept interpretations get really weird, but that's because it depends on the variable that we're looking at. In practice, when we're making predictions, are we ever going to have anybody who's 0 or 1 inches tall in our data set? No. You're born at heights greater than that, right? So sometimes the intercept will get kind of goofy, but we still just interpret it that exactly the same way, right? It's just that we know that yes, it's starting there when the X variable is 0, but in practice, we're not going to see any X values below, I don't know, 50, 40, however shortest person in the world is, right? Does that make sense? Is that clear what I'm getting at there? Okay. So you will have that occasionally pop up. So the next thing we're going to talk about is a statistic that we can get from Stata called R squared. Okay, so R squared is sometimes called the coefficient of determination. I'll probably never reference it as that the rest of the semester. I always just call it R squared. But the easiest way to think about it is when you have a variable, so when I had like that income variable, it has a certain amount of variation. There's a lot of things that are influencing people's income values, right? Maybe their, education level, maybe the number of days they use marijuana each month, but there's a bunch of different factors, okay? So our R squared says there's all this variation that exists in income. When we just try to predict it using the number of days of marijuana smoke or used each month, here's how much of that variation we can explain. Here's the proportion of that variation we can explain, and we then typically talk about it in terms of a percent, right? So you usually would say I can explain, the proportion I can explain is 0.2. Usually when you're conversing with people, you say the percent we can explain was 20%. Right? So we'll kind of go back and forth between the two. And the reason why we need to, know that it originally is a probability is because the way Stata gives it to us is not in percentage format. Right? But we can always go from decimal, right, probabilities to percentages by just moving that decimal 2 places. So the way it's actually calculated is we're first going to look at, here we've got our total sum of squares. What does this look pretty similar to? The numerator of, it's the deviation from the mean squared, add them all up. Yeah, they're scaring me. If I take the deviation from the mean squared, add them all up and divide by the total number of observations, that would give me my what? Yeah.
Is it the error?
So not quite our error, right? So our predicted, so this is going to be, our error is based off of our predicted y. If I were going through the data and I'm taking every single observation, I subtract the mean of that variable, I square it, and then add that up for every single observation, divide by the total number of observations, that gives me my variance, right? So scaring me a little bit. Hopefully these equations start to look kind of familiar. This looks like the variance without dividing by n. Now this is something we probably haven't seen yet, which is here's the predicted y values, their deviation from the mean, squaring that, right? So we can think about, there we go. This line of best fit was essentially the predicted values that we were getting for y for different values of x using our intercept and slope coefficient. So this represented our predicted values. We said, okay, I can predict a value for some x. I can predict that y value for some value of x, but the actual data might have a different y. So we had the difference between y and our predicted y. That was what we were calling our error term. So there's going to be some original variation that just exists in the actual y values. There's also going to be some variation that exists in our predicted y values. Okay? So what we're going to do is take the variation that exists in our predictions, the total variation that exists in the variable that we were trying to predict, and the ratio of those two will tell us how much our predictions are explaining. Okay? How much of that variation in the income was the number of days using marijuana each month explaining. So we would call this our explained sum of squares, generally ESS. Here's our total sum of squares, TSS, right? Just kind of shorthand. So R squared, when we calculate it, is going to be not in a percentage format. What's the highest my R squared could ever be? Yeah, it's someone holding up their finger, right? If my predictions were perfect, and I'm explaining all of the variation, there's no error, well, then the predicted y is essentially just the actual y values, and I get a ratio of 1. What's the lowest it could ever be? 0. I literally am explaining none of the variation with my variable. So we know that it's going to be somewhere between 0 and 1. The closer we get to 1, the more we can explain about that y variable with our x variable. Right? Any questions on that idea before we? So I'll kind of show you just some results so that we can get an idea about what this looks like in Stata. So I'm going to run this regression. I think we used this example last class, the number of bursts and the number of these shale oil wells. So just to get some more practice interpreting, we said, if a county has 0 of these shale wells, the predicted number of births would be about 6,100. That's interpreting our intercept. What if we wanted to interpret the slope coefficient? A 1-unit change in our X variable, so having 1 more shale oil well in our county would predict that births go down by about 3.9. Okay, that's our interpretations. However, if we look at this, what percent of the variation in the number of births in the county are we explaining by the number of oil wells or shale oil wells? Nothing, right? Now it's technically something, it's just to the 4th decimal, it's 0. It's like 0.00000 something. So what this is telling us is that there's a lot of factors that would be predictors of the number of births in the county. The one I can think is probably going to have a very high R-squared is population, right? If you have a higher population in the county, you're likely going to have more births, right? So if we're just trying to explain the number of births with these oil shale wells, we might not be able to explain much of the variation at all. There's probably hundreds of factors that explain some parts of the variation in Y, and we're only using one of them, right? So if we're only using one of them, it's going to be hard to get a pretty high R-squared. We're going to want to eventually be able to use a bunch of different factors. We won't get to that until next week. Okay, we're going to walk before we can run here. So this one looks like, yeah, this isn't a very good predictor. It's not explaining much of the variation. If I instead had a data set, and we'll pull this open here in a second, where I've got the cases per 100,000 or 100,000 cases per 1,000 people, and then I've got the percent vaccinated on the right-hand side there. So we had our estimates before we made our interpretations. What's the R-squared here? Well, at least it's not 0. It's not like the largest, but it's about 4.2%, right? The proportion of the variation we can explain is 0.042. Said differently, we're explaining 4.2% of the variation. Okay. Now, I told you it was the ratio of 2 things, which was the explained sum of squares and my total sum of squares. So we can get these values from Stata as well. And maybe on a quiz or maybe on a problem set or something, probably not a problem set, probably a quiz, I might leave out the R-squared and then ask you what the R-squared is. Well, if you have this information, the model SS here, so sum of squares, right? The model sum of squares is essentially the same as the explained sum of squares. The sum of squares that the model is explaining. Right? So here's our explained sum of squares coming from the model that we used. Now we used a very basic model, just one variable there on the right-hand side. And our total variation that existed in our Y variable, or our total sum of squares, is right here. So if you want to prove this to yourself, if you actually put this into a calculator, take that 43,000 divided by what, about 1,000,000 something, you should get that R-squared of 0.042. So you can always calculate it using those sum of squared kind of statistics. Okay. Any questions on that? So there's also something up here that is kind of interesting, which is our residual sum of squares. So this residual sum of squares is essentially the amount of variation that exists in Y that we can't explain. So when we see this term residual, it's really the same as error. It's the error term, right? The amount that we can't explain. So when we make predictions, so I can even use the income marijuana one here. We can make predicted values by plugging in different values for X, right? But when we look at the actual Y values, they will contain our prediction, but then also our predictions are sometimes off. They're also going to include this error term. So our predictions are going to explain this part of that Y variable. The residual, what we're not explaining, is whatever is in this error term. Right? So if our R-squared is relatively low, our residual sum of squares is going to be pretty high. Okay. Any questions on that idea before we keep moving? So this term of residual, it's really, you can think of it the same as just error, right? So it's the amount of variation that exists, not in what our model is explaining, but what our model, there what our model isn't explaining, right? Here's what our model explains, here's what doesn't. If we add these up, we get the total. Okay. Any questions on this before we keep moving here? All right. I think I'm going to go a little bit out of order. I was going to jump to Stata here, but I want to get through a little more material before we dive back into Stata. I think it'll just make a little bit more sense. So we've looked at two continuous variables as our x and y variable. So sometimes we'll be using what we call dummy variables or indicator variables. We've already kind of talked about creating them in Stata and then using them to find conditional means. But here we're going to say, what if we use them in our regression? So if our independent variable is a 1, 0 variable, so that right-hand side, so I'll try to use all these terms change between. The right-hand side of our regression are our x or our independent variables. The left-hand side of the regression are y or our dependent variables. So if we have a right-hand side, right, x or independent variable, that's a dummy variable. What's the interpretation of our slope, or sorry, yes, our slope coefficient. So if we estimate this, all I'm using is different notation to indicate there is some slope coefficient associated with this dummy variable. So the way that we would interpret this is a 1 unit increase in x. Well, now if it's just a 0, 1 variable, what's a 1 unit increase? Going from the 0 group to the 1 group. So it's essentially the predicted difference in between these two groups, y value. So show you a slightly different way. I think I've got this in the slides, but I think it can help here. So let's say I've got height and I've got this indicator variable for whether or not the person is considered male. All right. If I'm thinking about what this looks like, it's kind of goofy, but here I've got my x variable, here I've got my y variable. What's the predicted height for someone who's not considered male? Just the intercept, right? So here, this 0 category, I usually put the 0 in the same one, so I could, plot it. Here's the 0, 0 point. There's my intercept coefficient. Oh, sorry. Now, if I'm thinking about my slope coefficient for the dummy variable, what that's telling me is if the individual is considered male, what gets added into my prediction? Well, now it's going to be beta 0 plus beta 1, right? So for the 1 group, I would have a predicted value up here. Now it's not nice and continuous, like I can't really have like this nice, like a scatter plot because I only ever have 0s and 1s, right? So I'm only ever coming up with 2 predicted values. This is the most interesting if I were to run a very simple linear regression with a dummy variable, but we will want to start to include these dummy variables later on, and we have a little bit better of a visual of exactly what they can do for us, right? We'll be able to pick up differences across groups in these various effects. But for now, if I were just run it with a dummy variable on the right-hand side, it's telling me about the difference in the predicted y value for the 0 and the 1 group. So the way that we would interpret it as males, the 1 group relative to females, the predicted increase in height, predicted height would be whatever beta 1 is. So our 1 unit now is just going from the 0 to the 1 group. And I think I've got a couple other examples here. So we'll just go, I think I've got this up here, basically what I just did in the board, right? It's going to give us kind of that difference in between the 2 groups. I just used beta subscript d here to represent this is a dummy variable, but it's still a slope coefficient, right? Here, I think I've got another example here. So here I had an example where I had this 1, 0 variable for if they were considered a student athlete at the university. I have a college data set that has like a bunch of, we'll use it later on in the semester as well. But it has their college GPA and whether or not they're considered a student athlete. So how would I interpret my intercept? It would be if my x variable is equal to 0. So for a non-student athlete, the predicted GPA would be 2.66. For someone who's considered an athlete, right? Going from that 0 to the 1 group, someone who's not considered an athlete to being considered an athlete, that's my 1 unit change. The predicted decrease in college GPA would be about 0.28 points. So what also does this concept, here we've got those interpretations. Now, obviously, we're not controlling for a lot of other factors here. We eventually want to be able to do that, but we've got to walk before we can run. What would this constant also represent? So if it is when the students are considered non-athletes, the predicted GPA would be 2.66. What do you think that might also be equal to? Another statistic we've already talked about in prior weeks. Well, I've only got two groups, athletes and non-athletes. So this is telling me the predicted GPA for all of my non-athletes is 2.66, which means that on average, their GPA is 2.66. If I were just to run this simple regression with just that dummy variable, my intercept is actually going to tell me the average GPA of my non-student athletes. When I add these together, right, take the intercept and then also that dummy variable for what the group that was student athletes, what would these add up to? The average GPA of my student athletes. So I run this very basic, one dummy variable on the right-hand side. I can actually parse out my means here. That's all the regression is actually telling me. Here's the mean for my zero group. Take that, add to it that dummy slope coefficient, and that would be the mean of my one group. Okay. Is that any questions on that? Is that clear? Okay. And maybe in the data, we'll kind of prove this to ourselves here later on if we have enough time. So what if our dependent variable, this is where it gets kind of tricky. What if our dependent variable is a dummy variable? So now our y variable is just a 1, 0. What are the units of that dummy variable going to be? Well, if I'm moving from the 0 to the 1, I'm changing the probability that I belong to that one group. Excuse me. So we can make predictions about whether or not someone is a student athlete or not, right? But our prediction is going to be, there's a 60% chance that they are. Or when we run the regression, everything in our regression is always in terms of probability. So there's a probability that they're a student athlete of 0.6. So I think the example I have here, I think makes it more concrete, is what if I were to run a regression where I had 1, 0 variable for whether or not it was considered a metro county. My X variable is this unemployment rate measured in the units of the percentages. So 3.5%, 2.9%, that's my unemployment rate. So now how would I interpret this slope coefficient? Right? This is going to be that as that unemployment rate variable goes up by 1 unit, so as the unemployment rate increases by 1%, the predicted change in my Y variable is 0.045, right? But what's the units of my Y variable? We said it's probability. So having the unemployment rate be 1% higher would predict that the probability that it's a metro county would go down by 0.045 or go down by 4.5% if we want to kind of convert the way that we typically talk. But saying in terms of the probability, if that's easier, that we can do it that way as well. Okay. So what's my interpretation here? For every 1 unit change or 1% change in this unemployment rate, the probability I belong to the one group, or was considered a metro county here, decreases by about 0.045. Okay. So it's easier to think about it that way. Dependent variable is a dummy variable. Changes in the Y variable, the units is probability. Changes in the probability. Okay. Anything else I want to mention here? Not the most predictive thing. R squared is relatively low. There's still a lot of variation in whether, why it's a metro county, a lot of other factors that probably explain more of the variation we see in that Y variable. But this is just kind of an example that I have in the data set. We're using some actual variables to look at. So just to be complete, how would I interpret this intercept? Well, it's going to be when the X variable is equal to 0, right? So an unemployment rate in a county is equal to 0. The predicted probability that it's a metro county would be about 0.6. So once again, still in terms of probability. Any questions on this before we keep moving? Shouldn't be too bad. Yeah.
Is there any way to tell from just the output that the predicted value, that we're looking for probability?
So not the output. Nothing in this output would. What's going to tell you that Y variable, that the units is a probability, is if you look at the data and you hit tab and it's just zeros and ones.
Okay,
Now, for most
Yeah.
examples, it's gonna be pretty odd, like it's either a metro county or it's not. Alright, you either have a college degree or you don't, like it's gonna be this like binary. You wanna think that's another term you could use to reference, so you'll see it in the data, it's just a variable with ones and zeros.
okay, thank you.
Good question. Well, we'll come back to this, we'll play around here in this data set a little bit, so where I was getting all of these kind of different, a lot of these regressions. Was from a COVID county data set. So here I've got my global, I had someone stop in there, if you don't want to use this. Well, the only reason I kind of explained this to you even week one and we were introducing this idea is that if you were to have like your file, whatever your folder is called, so for a lot of you, you wouldn't have this, you would just have like this, and instead of fall course material, it'd be like 371 files. It's just so that you can run this code where I use path and it will run for you. You can always go to file, open, and open the actual data file. You can always do it that way. It's just that for those of you, if it is easy for you to use this path, you can just stay in this do file, right? You don't have to kind of go back and forth. So I'm gonna define mine right now. I'm gonna go down here and I'm gonna kind of get that COVID data set opened up. So just some other examples here. I've got the number of cases of COVID that a county had and its population. So what do you think is probably true about that one? I guess I buried the lead there, but if I run this regression, notice I get a very high R squared, 0.95. Why? Because the higher the population, like out in rural counties, there's just not as much spread of the disease as when you're looking at inner city New York, right? So if we just use the population, it explains 95% of the variation we saw in COVID cases across these counties. Okay. So this would be one where, looks like this is probably a pretty good predictor, right? It's going to be able to explain a lot of the variation. So if we go back, we could also do some of these other things that we talked about. So here I had one, which was, here's the number of new cases. And here's whether or not that county was considered to be in the South. So I don't know, these are some things I thought maybe in the South, people are out and about more, they're not cooped up inside, and germs aren't spreading. So we can kind of look at that. This is where we're going to have a dummy variable on our right-hand side as our X variable, right? So I look at this, the interpretation would be, if the county is considered to be in the South, the actual predicted number of new cases they would expect is 892. So it actually went up. So it went against my original intuition, right? Now, we're not controlling for a lot of other factors. This is still just evidence of a correlation. Next week, we'll start to talk about how we move towards finding a causal relationship. And also our R squared, how much variation in the number of new cases are we explaining with if it's in the South? 0.002 or 0.2%. We're not explaining much of the variation there, right? So it's probably not a great predictor to use based off of off of that factor. We can also do, cases per person in the South, cases per person from vaccinated. We run both of these. Which ones are better predictors? Well, I can kind of compare the two. I've got the same Y variable now, so it's cases per 1,000 people. So if the county being in the South, is that explaining more than the percent of the county that's vaccinated? Well, here, number of cases per 1,000 people, I'm getting an R squared of about 0.17. Whereas the percent vaccinated, I'm only getting an R squared of 0.04. We would say just based off of the R squared, this is going to give us slightly more accurate predictions, right? We're explaining more of the variation in that Y variable cases per 1,000 people than if we used that vaccinated variable. Okay. So just comparing the R squared, as long as you have the same Y dependent variable, you can kind of look at, okay, which of these variables is explaining more of the variation. Okay. Any questions on that before we keep? Also, I'm not aware of a way. Yeah, I'm not aware of a way you can like blow this up. And so if you're having a hard time seeing it, this is why I kind of give you the do file so you could have it kind of run on your own computer, kind of see it right in front of you. I'll mention the values obviously, but I get that these are kind of small, but 0.17 versus 0.04 here. I also had this regression that I just thought was kind of worth pointing out. So I'm going to create, we've done this before, but I'm going to standardize a variable, right? So originally, maybe I run a regression where my dependent variable is now the percent of the county that got vaccinated and the median household income. So I try to do some of these things. They're a bit stereotypical occasionally, but I'm like, yeah, well, higher income areas might be more or less likely to get the vaccine than others, maybe more or less likely to trust the government, maybe more or less likely to even care about getting sick, right? So maybe there's some correlate, right? Maybe there's some relationship there. So if I run this regression and I looked at kind of the relation between vaccinated and household income, I could get that coefficient. Well, now notice a 1 unit change in X here is really small, right? $1 more in income, household income, the effect size is going to be really small. Reporting this doesn't have a lot of relevancy to if you're telling someone this, like, I can't really envision this. Having $1 more as it increases the percent vaccinated by 0.0003. Okay, but what if what if we had like $1,000 more and then you have to start scaling it? So it sometimes makes a little bit more sense is standardize your variables. So we're just going to create the mean of that household income. We're going to create a variable which is the standard deviation of that household income. And I'm then going to create this new standardized variable where I take the original income value, subtract the mean, divide by the standard deviation. All right. So we'll run this. I'm now going to run this regression, right, where I'm using the standardized value of income. Oops. There we go. So actually, I want these to be stacked. So I'm going to run these again so that I can just scroll back and forth. So here was here. We're going to run these two. So they're stacked right on top of each other. So if I look here, when I didn't standardize the variable, I had that really small effect size, really small coefficient. My R squared was 0.11. If I instead scroll down, notice my coefficient now is much different. I still got the same R squared. So standardizing it, I wasn't like adding any new information. I'm not able to explain any additional variation. But now the interpretation, I can say a household that has 1 standard deviation above the average income would expect that county to have about almost 5% more of its population vaccinated. That is a little bit more of a number that people can kind of process, right? The everyday person. So standardizing a variable sometimes has some value to us. Okay. What else do I want to do here? There's something. Ignore this. We'll come back to this. I don't think there's anything else I want to. We did this one in class. We could do different examples. I think I've hit probably enough that we've gotten a lot of interpretations in. The other thing I want to do at this point, and I don't think this is, I didn't put this on Canvas yet. I will if you're interested. But last night, sometimes I have these ideas and I can't let it go. Okay. When I have frozen state up. But I'll put up a new regression in class file where I added some stuff at the bottom. So jumping the gun a little bit, but remember when we talked about finding a sample mean? So we said there is some distribution of our sample means, and it's going to be centered around whatever that true population mean is. Okay. We then said, okay, if we take a sample, we're going to see some sample mean. We can then turn that into a test statistic, right? It could come from the student t or the standard normal. We could then find a p-value, right? And go through the whole process. Okay? So with this idea in mind that the sample means were normally distributed around that true population mean, we could think of the same sort of thing is going to apply when we take samples and then run regressions. So we take samples and run regressions, the coefficient values we're seeing are, we kind of put a hat above them because could make like Y bar, like beta hat. This is just saying this is an estimate from a subsample of the population. So it'll end up being true as long as we have these sample sizes over 30 that central limit theorem's met. We'll end up, like let's say I went out and took 1,000 different samples and I ran the regression for same variables. I find that slope coefficient. I now have 1,000 different slope coefficients. I plot them out. I'd end up with a normal distribution where they're centered around whatever that true slope coefficient is. Okay, so get a little bit more of this before we look at this data here. I think there's a couple slides that'll be helpful for us. So we already talked about dummy variables. Here we go. Oh. So the expected value, that thought experiment, where if I can take 1,000 different samples, all of those estimates for what that slope coefficient is, the mean of them, or the expected value, will be whatever the true population beta is, whatever the true population relationship is between this X and Y variable. Now, we have something else that looks kind of similar to a standard deviation. So with those sample means, we said our sample means will have a standard deviation, which is the square root of the original variance of the data we sampled from over our sample size. We have a very similar thing here, which picks up the variation that exists in those 1,000 different slope coefficients. We just, when we get to regression, we reference it as our standard error. It's calculated a little bit differently than our sample variance. So remember, when we're doing sample variances, how there's like that n-1. This is probably getting a little bit into the weeds here, but it's because we had one variable to calculate that variance or to calculate that statistic. Well, when we're running a regression, we actually have two variables. So we end up with a n-2 there, right? And then once we get to multiple linear regression, it's not just n-2, it's n minus the number of variables we include in the right. It gets more complicated. We're never going to have to do this math by hand. I'm never going to make you kind of grab these values from state output. All I want you to know is when we look at all these different samples slope coefficient estimates, there's going to be some mean, and the mean will be whatever the true population slope is. And there's also going to be some type of standard deviation, right? Or standard error. Like I said, it's not correct technically to call it standard deviation, but if it's easier for you to kind of connect with it that way, you can think of it like that. Okay. And then the same sort of thing applies as when we were thinking about the standard deviation of our sample means. Remember, I said we would take the original variance divided by the sample size. So as our sample size went up, that standard deviation for our sample means was getting smaller and smaller. Same thing would happen here. The larger the sample size we have, this fraction becomes smaller and smaller. We're getting a lower standard error on that sample coefficient, or a lower standard deviation, if you want to think about it that way. Okay. So once again, as long as we get that central limit theorem met, it should be normally distributed, and we should know that these things are going to hold as well. That the mean of our sample slope coefficients will be the true slope coefficient. Now we talked about statistical significance. We could do the exact same thing with this. Before we do that, I want to prove to you, I guess, with the data. I think this is kind of worthwhile, worth seeing. And I'll explain what it does to you. I would never expect you, what I'm about to show you is not something I will expect of you on a problem set, okay? But I'll walk you through this, okay? So when I was looking at that county level data, technically I had population data. I had every county in the US for that time frame. So I could run this regression where I looked at the cases per 1,000 people and the percent of the county vaccinated, run that regression. And because it's population data, I can think of it as this is the true slope coefficient, right? This is what the true estimate should be, or not estimate, sorry. This is what the true value should be. I can then take subsamples of that and find estimates of that value. So I'm going to go here. I'm going to define this program that uses that COVID county data, randomly samples 30 of the counties. It then runs a regression for this just sample data, saves that slope coefficient. I tried to call it, I didn't call it beta 1, but B1 here, right? I'm saving that slope coefficient. I'm then going to do that. I have 100 in here, but I don't think it'll bog it down too much. I can do this 1,000 times, right? Once I do this 1,000 times, I'm going to have a new data set that has all of the 1,000 different estimates I have for that slope coefficient. What should be true once I have all those is the mean of all of those estimates should be equal to the original value I found using the population data. So we'll see if that holds, right? And we're barely getting the central limit theorem met here. Technically, you know, we should be over 30, but we'll see if it works. So I'm gonna come down here, run all this code. It's gonna take a second. It's doing this 1,000 times, storing all of them. We'll see if it's done. There we go. I'm then gonna take this new variable, and I called it means. I probably should have called it like betas. In fact, I'll change it when I upload it to make a little more sense. So I can call this betas. I'm gonna summarize that variable that had all those stored slope coefficients. Hopefully, the mean of them is exactly equal to that true value of negative 0.25. So we'll see if that holds. Pretty darn close, right? I mean, to the fourth decimal, we're off. Our third decimal, I guess we're off a little bit. But you know, technically, in order for me to get the exact value, I can't just take 100. I'd have to take an infinite number. So you can never truly prove this to yourself with data, but you can see here that if I were to just continue to run more and more simulations, I'm going to be getting closer and closer, right? And I could do 10,000, although it's going to take too long. I don't want to waste class time doing that. But you can see here that that holds. Now you can also do higher sample sizes. So here, where do I want this? This isn't perfectly the same thing, but we said you can think of all those 1,000 different slope coefficients. I could also find the variation that existed in them or the standard deviation. So that's what, 0.237 here. I said, if we take higher sample sizes, what should happen to that standard error or that standard deviation? Just like with the sample mean, the higher the sample size, the denominator is getting larger, so the standard deviation or the standard error will decrease. Yeah, someone's pointing down, right? So I'm going to run the same thing, but I'm going to randomly sample 100 people here. Now, when I get that, okay, I got the exact, or you know, not quite the same. It's very, very close, negative 0.25. It's off of the third decimal. What's happened to the standard deviation? Well, before, when I only had samples of size 30, it's 0.23. Now it's 0.1, right? So all these things we can kind of prove to ourselves running these simulations with a data set. Now, in practice, we usually only have like one sample data set, right? So if we only have one sample data set, we're going to go back to thinking about doing hypothesis testing, okay? So let's assume we were thinking of that those sample means. When we do hypothesis testing, we said those sample means are normally distributed around what value? Not the true population mean, we don't know what that is, but around, yeah, some assumed true mean. Right? Now, for us, luckily, when we do this hypothesis testing for slope coefficients, it's always going to be a two-tailed test, right? So we don't have to worry about the one-tailed test anymore. What did we do in practice? Well, we only had one sample, so we calculated a sample mean. We then wanted to say, okay, based off of this sample mean, it's not the same as the assumed true value. Can I reject this? Right? So what did we do? We turned this into a what? I turned my sample mean into a test statistic. Now, how did I do that? I took that sample mean value, I subtracted the assumed true mean, and then I divided by the standard deviation of that sample mean, right? So this was how we found our test statistic. Then using that test statistic, what's the next thing I find? So this would essentially represent, so I'm writing T here. When we're talking about the sample mean, we were using the Z tables to kind of approximate. But remember in practice, if I do have sample data, technically I'm using the student T distributions. Now, when we're doing this by hand, I kind of let you, or I told you, you could just use those standard normals to approximate. When we look at the output that Stata gives us, it can actually use the specific student T, the correct student T, so we don't have to approximate. So yes, we've calculated already our Z value or T value. This is our test statistic. We then use that to find what? There was two approaches. One approach was the critical value approach. That one's not as useful for us when we look at slope coefficient estimates. The other was the what approach.
the p-value.
Yeah, so I can use this. Look it up in the table, find the area to the right of it. Now for a two-tailed test, this is not my p-value. What do I still need to do? Not divide by 2. Here, if I say it's equal to a value, I found sample evidence over here, but it would have been equally as likely if I were, I only have one sample, but if I were to take more, it would have been equally as likely for me to see values that went against the null down here. So I can find this area. I then need to do what? Multiply it by 2. That would give me my total p-value. Okay. So this is still like review, right? But we're then going to kind of take this and what does that look like for our slope coefficients? So for our slope coefficients, I said we're going to kind of make it easy in the sense that we're always going to be using that true slope coefficient is equal to, and here I'm going to not write beta 0 because it gets complicated because that's the intercept. So we're going to be saying is it equal to some value, and the value that we will always use in this class will be 0, right? And I'll talk a little bit more about why here in a second, but the value we're always going to use is 0. Okay. So if I'm thinking about the distribution of my not sample means, but my like sample slope coefficients, the estimates that I'm getting from my sample data, they should be centered around whatever that assumed true value is. Here we're always going to use 0. So I'm then going to think about, I'm going to see a very specific estimate from my regression, my one sample that I have. I'm going to turn that into a test statistic. Now it's not going to be coming from the standard normal, it's going to be coming from the student t. Now, when we have large sample sizes, we can approximate it with the standard normal values, but we'll see once we get to the data output, it's going to give me the information from a student t distribution. Okay, so I don't have to worry about using that t table. It's going to do it for me. So once I have that, Stata can tell me the area to the right of it, multiply it by 2, and report to me the p-value. Okay. Now it goes back to just like we were doing before. Can I reject the null? We only reject the null if the p-value is what? Relative to our alpha thresholds. Less than. We can think of these alpha thresholds. And someone stopped in my office. I think this might be helpful for everybody to see. Essentially, we were saying these are the cutoff probabilities we're okay rejecting the null with if the probability of seeing the sample evidence we found, the sample statistic with the sample slope coefficient, falls below this value. If the likelihood that we saw this estimate for the slope coefficient falls below 0.1, it's a pretty low probability that we saw that, then it's probably true that this isn't the real value, right? And in fact, the real value must be something probably a little bit higher. So we said this was synonymous with thinking about the 10, 5, and 1% significance levels. If you read academic papers that you generally talk about rejection decisions, they don't say you reject an alpha of 0.1, they say you reject the 10% significance level. You may also see in more mainstream media, or when things are put out to the general public, it's generally said we can reject the null with 90, 95, or 99% confidence. Right? So these are saying really the same thing, just in a slightly different way. Okay? So we're ultimately going to want to know what levels of our conventional 3 levels can we reject the null at using this p-value. Okay. Any questions on that before we keep moving? We'll look at some Stata output. How do we actually get these? We don't have to go through this process every time. It's actually pretty nice, right? So, there we go. So let's go back here. So we're always going to use this assumed true value of 0 for this class. In theory, you can do one-tailed tests. You can use values other than 0. I'm only ever going to make you, when we're looking at these slope coefficients, assume the slope is equal to 0. You'll have a two-tailed test every single time, and then assume true value will be 0. So the reason why this makes sense is because whenever we're trying to estimate relationships between 2 variables, our y and x variable, we're trying to see, well, we think there's a relationship. So the idea of the null hypothesis was that we stack the deck against ourselves. If I think that it's not equal to a certain value, I assume it is equal to that value and try to disprove it. Okay? So here, we're always going to start out assuming that that slope coefficient is 0, which means that there's no relationship between x and y. If we can find strong enough sample evidence to reject this, then what we're saying is we can reject that there's no relationship, or we found strong evidence that there is a relationship. Okay? So what's this going to look like? The steps are literally exactly what we were doing before with hypothesis testing. Here I've got kind of the critical value approach. The p-value approach is going to be way easier, and I think you'll see why in a second, right? But it's the same process as what we used before. It's just that calculating our test statistic now is going to look a little bit different, right? So before we had what we took our sample mean, we subtracted the assumed true mean divided by the standard deviation. Well, now the statistic we're looking at is no longer the sample mean, but our slope coefficient estimate that we got, right? Our assumed true value for that slope is always going to be 0. I put often here. For us, it's always going to be 0. And then our standard deviation is no longer the standard deviation of the sample mean. It's our standard deviation of that slope coefficient, or what we said was the standard error, right? How can we get these things? Well, here's the actual equation behind the standard error. We were looking at like the difference between the actual and predicted y's, squaring, adding them up, divided by n-2. So it's a little bit different, right? But we're never going to have to do this by hand, right? But like I said, if it helps, think of the standard error. It's like the variation that exists in the estimates for this slope coefficient. So if I were to run a regression, notice next to my x variable, I've got this line. So I've got my coefficient estimate. I've got my standard error. That assumed true value is 0. How do I get my t-value or my test statistic? It's just that coefficient divided by my standard error. So notice here, if I take that negative 253 divided by 48, it's approximately -5. Sure enough, -5.23. That's how it's coming up with that t-value. It's going to always do that for us. So on a quiz or something, I might leave this off and expect you to know that you could calculate test statistics by simply taking a coefficient and dividing by a standard error. Right? And our kind of benchmark values are going to be pretty much the same, right? Because we're always going to have pretty large data sets like 5,000. You know, I'm really looking for values that are above, 1.65, 1.96, 2.58. Those are our 3 kind of conventional critical values, right? So large data sets, we can kind of use those standard normals to approximate. But we don't have to approximate because Stata will use that student t distribution and look up the actual p-value. Now notice here, what's the p-value associated with this estimate? Basically 0. So what levels can I reject the null at? 10, 5, and 1%. Which ones can I reject? All of them, right? 0 is less than 0.1, is less than 0.05, and is less than 0.01. Okay. Any questions at this point before we keep moving here? Yeah.
I have a question. So under the -5.2, the 96.7, what is the significance of that number in comparison to like the t above it?
So down here, this would be the test statistic for our intercept coefficient.
Okay.
Right? So it's saying, is that intercept coefficient, whenever we can reject the null, we call that the estimate is statistically significant. Right? So here, both our intercept and our slope coefficient are statistically significant. The fact that this is 96 tells me that, if I wanted to break this down, maybe I could reject that one at the maybe at the 0.00001% level. This one, I'm guessing I can probably get out to like, 0.005, or something like that as my alpha. So the higher the test statistic, we're just moving further towards it. So what's happening to our p-value as the test statistic gets larger? P-value is getting smaller. Okay? So larger test statistics, it's more likely you can reject the null. But the actual relevance of saying the intercept is statistically significant doesn't have a lot of meaning for us. Yeah. So same rules apply. Reject when the p-value is less than alpha. So we've got a second one here that we were using earlier in the class. Notice here my test statistic for number of bursts in these oil wells. negative 3.9 over 81, I'm getting a test statistic that's basically 0. Right? The value I found, given the variation that exists in the data, isn't that far away from 0. In fact, it's 0.05 standard deviations away. That's not very far. So what's going to happen to my p-value? Well, I didn't see something very far away from this assumed true value of 0. So the probability I saw is going to be relatively large. Sure enough, my p-value is 0.96 here, right? I'm not going to be able to reject at any level. And this is just, we already did this kind of interpretation earlier. Any questions on this before we keep moving? Okay. Get out here, 12:45. I'm not going to waste time with these one-tailed tests. I thought if we had time, maybe I would. I'm never going to make you use these. In practice, you could. So let's say I had like height and weight. I inherently know that that relationship has to be positive, at least on average, right? And so I might say, okay, for every additional inch taller someone is, what's the predicted change in their weight? Maybe I don't want to start out assuming it's 0. I know that it's going to be a positive relationship, so maybe I want to do a one-tailed test. And maybe I don't just want to do 0. Maybe I want to say, is it greater than, 2 or 3? I can use values there too. I'm never going to make you guys do it. If you want to do a one-tailed test, where you still keep using that same assumed true difference of 0. The only difference is going to be that Stata reports to you always the p-value for a two-tailed test. So if you have the p-value for a two-tailed test, how do you find the p-value for a one-tailed test? It's just literally would just be half of that, right? Because part of the process to find the p-value that we worked through was I find the area that more extreme than the test statistic I found, I then multiplied it by 2. So if I'm going to a one-tailed test, I just wouldn't have multiplied that area by 2. But we don't really have to worry about them, but I wanted to kind of be complete in talking about these things and kind of just mention that. What I do want to make sure we get through today, and we should have plenty of time, is just like with sample means, we created these confidence intervals. Now, I think the questions that I was asking you to create them, you could use the standard normal values to approximate, and then we'll still get counted correctly on the quiz. So you were just using that standard normal. But technically, we should have been using the student t distribution if we wanted an exact amount. So how do we find a confidence interval? We took our sample mean, we went a certain number of standard deviations to the left and to the right. How many standard deviations? Well, that depended on what level of confidence we wanted to make the statement with, right? Whatever our alpha value was. So we would have half of alpha on either side of our confidence interval. We could then determine how many standard deviations out we need to go to get that half of alpha on each side. Take our sample mean, add and subtract that number of standard deviations times the standard deviation of that sample mean or our sample statistic. It's going to be the exact same thing for our slope coefficients. We'll find this estimate, negative 3.9. We're then going to go a certain number of standard deviations to the left and to the right of it. So this is the number of standard deviations the way we're going. Once again, our standard deviations of these slope coefficients, we reference that as our standard error, right? So we'll take this, add and subtract a certain number of standard deviations away to get our upper and lower bound. Now, Stata always defaults to the 95% level. Some of you working on your problem sets, I think, got a little confused and were like, Google searched and found a way to change it. You can change the confidence interval that you get from Stata, right? But when you're making rejection decisions, you don't need those confidence intervals because once you have the p-value, you can look at any level you want. Now here, if I left off the p-value and said, can you reject the null at the 95% level here? I just gave you the confidence interval. Remember what we're saying with these confidence intervals is, with 95% certainty, the true population slope coefficient value should be between these two values. Well, what was the hypothesis test we were always doing for this coefficient value, slope coefficient? We always assumed it was equal to 0. So if 0 is within the range of our confidence interval, that could be one of the possible true values. We shouldn't be rejecting it. So in this example, notice 0 is definitely in my confidence interval. So what happens? I failed to reject the null, right? It could be one of the possible true values. Another example, right, where we have the berths and oil shell wells. Now, if I'm looking at this, it does include 0 as well. So what should I be making? This is the exact same. Yeah, sorry, this is the exact same thing. I tried to jump the gun, but right, 0 is in my interval, so I end up with a really high P value. I can't reject 0, right? It could be one of the possible true values. More interesting here. What if I have something like this? So I've got that marijuana usage income example. Notice here, my 95% confidence interval only includes negative values. So with 95% confidence, I'm saying the true slope value is somewhere in this range. So would I reject or fail to reject that assumed true value of 0? I'd reject it, right? It's not in my range of possible values. Sure enough, if we just use the p-value to make our rejection decision, p-value is less than the alpha, definitely less than an alpha of 0.05, we reject using the p-value approach as well. But if I left off this p-value and only gave you the confidence interval, you could tell me that I can reject the null for this slope coefficient because that assumed true difference of 0, not difference. Sorry, assumed true value of 0 is not in my range of possible values. I can do the same thing for the intercept here too, right? It only includes positive values. Okay. And in fact, if I wanted to do anything other than 0, just for the sake of kind of thinking about this, could I reject that this slope value was negative 100? Well, at the 95% confidence level, is negative 100 in the range? No, it's actually outside of it. So if it's outside of it, I actually can reject that value. I can reject 0, I can reject negative 100, I can reject negative 157, I can reject negative 350, right? Anything outside of my confidence interval, I would reject all of those values for a two-tailed test, which is always what we'll do. Okay. But you know, I can also see that through the p-value approach as well. Okay. I have this kind of catch-all categories to talk a little bit about, kind of summarize where we got to today. Let me see if there's anything else I wanted to do down here. I'll hold off on this next class. So yeah, we'll finish up with this. So just a general discussion of as we start to look at a lot of these examples, what do we actually care about? So when we're talking about can we reject the null, that's what we call statistical significance. I can say that I ran this regression and there is a statistically significant relationship between the number of days using marijuana and income, right? Now, I might have statistical significance, but you know, for every day, but I can expect $250 less. I mean, that's not a huge, percent of someone's income. Does that actually have economic significance, right? So I can find a statistically significant effect. That doesn't necessarily mean that it's going to be large, right? So if I told you, having an additional year of education increases your expected income by $10, statistically significant. But is that economics? I mean, going through college and only making 10 additional, that's not a large economic significance, right? So ideally, right, and we can have it go either direction. Sometimes we find things that aren't quite statistically significant, but if they're a really, really large value, they have a lot of economic significance, we don't want to just ignore them. Like let's say we ran something and we end up with a p-value of 0.12. We can't actually reject the null at any of our conventional levels, but we basically wouldn't be able to reject it with the 90% level. But if I had a p-value of 0.12, I could actually reject if the alpha was 0.13, and that would correspond to 87% confidence. Should I just be completely ignoring that? Especially if that estimate is really, really large. Especially if, like on that college degree, instead of 10, what if it was 100,000, right? Or something really, really large. Well, we don't want to just completely dismiss it. Now, ideally, we'll have both, right? We'll have an estimate that we can say is both statistically significant, but also it's a very large estimate, right? It's going to have economic significance as well, okay? So we'll, as we work through examples, we'll kind of think about this issue a little bit more intently kind of moving forward. But hopefully you can see the connection and the corollary between what we're doing with sample means and now what we're doing with essentially like sample slope coefficients. We don't generally call them that, but I think when we're first starting to talk about that, maybe helps it make a little bit more sense. Okay. So to kind of keep us in line with the other class, I think I'll probably kind of stop there. We'll finish up the rest of these slides on Tuesday. I'll then start kind of on multiple linear regression. So those practice problems, I think maybe a couple at the end might look kind of weird or sound weird because we still have a little bit more to go. But if you want, you can start looking at that next set once you finish that first quiz. Other than that, is everybody in here, anyone still having any issues with Stata? I think we've got most of them ironed out. Okay. So I unfortunately, although early in the semester, there's been a lot of times where I moved office hours due to the holidays and things on Fridays. I will not be physically able to be at campus tomorrow. So if you do have questions before you take that quiz, I'm going to try to answer them via email, possibly set up a Zoom for early tomorrow morning, sometime in the morning if you wanted to. Other than that, problem set Monday, I'll be in my office hours as usual. Those of you that stop by, I think it's been, been pretty good, pretty effective for you. So there's no more questions for me. All right, you guys have a fun, safe weekend, and I will see you on Tuesday.